So the subject is, I want to take something which I'm drawing symbolically like this, a tense. So I'll explain this in more detail, but it's a union of four toric surfaces. So this is T. It's four surfaces like this, so think of it as and I want to show how to deform to a toric fourfold, which is going to be called VAB. Right? And so the problem is here that this is at one of these axes. This is a union of two surfaces meeting like that at one of these axes. And I want to change that to something like this. Right, so I want to do something like this at each of these axes. So I want so that the top two axes are smoothed and the bottom two axes are made irreducible. So you know, here I've got something like local equation, something like xy equals 0 and replaced by xy equals a times z to some power. Yeah, so this is singular along the z-axis, whereas this one here is, of course, it's singular at the origin, but it's smooth along the z-axis. Right, so I gave a little hint about how to do this last time with, I had, I think, something like, if I have the surface 1/2 of 1, 1, right, this might be something like this, where this is a surface, it's got these two coordinate axes, it's just the ordinary double point, and on it it's got coordinates x0, x1, x2, with x1 squared equals, x1 squared equals x0, x2, and here I have another surface with coordinates x2, x3, x4, and I have x2, x4 equals x3 cubed, and these are in, this one is in A3, and this one is in A3. Right, and you know, in addition to these equations here, which are real equations, I also have some statement saying that the two copies of A3 are linearly disjoint. So that's saying also x1, x0, x3, x1, x3, x0, x4, x1, x4 equals 0. Right, and then I explained a bit last time that, right, instead of having x, I can change to x1, x3 equals the deformation parameter times x2 to the power of 4, and then I get this kind of picture like this, where I have a reducible surface, and then in the neighbouring fibre I get something which is still singular, but now it's this 243 guy. Yeah. So, and I have to change these equations. All of these equations have to be manipulated a bit. But the essential equations are this one here at x1 and this new one here at x2, right, where I've changed the equation. So I'm starting off with a surface that looks like this, a union of, this is an open tent made of two surfaces, and then I'm putting it in a bigger family, in a threefold, so that the general fibre, this is when A is 1, this is an irreducible surface, an isolated singularity. Okay, so let me say what I want. I want to set this out in some detail, because we're going to be Gavin and I are going to be talking about this for the next 3 or 4 lectures. So I want S1 to be the surface 1 over R of alpha comma 1 with coordinates x0, x1, and so on, up to xk, defined by R over R minus A is A1, A2 to AK minus 1. Yes, so this means that, sorry, this is alpha. Yeah, so I have the coordinates here are x0, x1 up to xk. I have equations x1 to the a1 equals x0, x2, etc. Right, and these exponents here, these are called tags, are these numbers here. Yeah, and there are other equations as I've described before. Right, and this 3 is going to be 1 over R with 1 beta, and I'm going to make a tent like this. So this is a union S0, S1, S2, S3, union, so S0 is C2, but it's C2 with coordinates x0, y0, and S2 is also C2 with coordinates x, k, y, l. Right, and so here R over, I'm sorry, this is S. S over S minus beta is B1 up to BL minus 1. Yes, and so you know, these are surfaces. So S1 is this surface here. S1 is the surface quotient singularity like this, with these coordinates, and this guy here is the x0 axis, and this guy here is the xk axis. Right, and so not a geometric part of this, but the coordinates on here are these x1 up to xk, which is sort of somehow the intermediate between x0 and xk. Yeah, so this is the standard toric description of cyclic quotient singularities that I've already mentioned many times. Right, and we're going to draw these. We draw these monomials like this. So this is not a geometric picture. This is a picture of in the toric lattice. In some eventually it's going to be in some toric lattice, right, with x0, x1, x2, xk, y0, y1, yk. Right? This is just a way of keeping the information, right? And I'm going to write a1, a2, up to ak minus 1, and b1, b2, bl minus 1. Okay, so this is notation for the set of equations so xi minus 1 xi plus 1 equals xi to the power of ai, and similarly yj minus 1 yj plus 1 is yj to the power of bj, and xi yj equals 0 except 0, 0 and kl. Okay, so the thing I'm telling you is here is my surface S1. It lives in space of these parameters x0 up to xk. Right? Then I'm taking a transverse copy of coordinate space with coordinates x0 up to y0 up to yl, and so this is the space. The space is in. This is in the tent T is S0 union S3 is contained in A k plus L plus 2, C k plus L plus 2. Yes? And the surfaces here are glued along the xk axis. So S1 contains this xk axis and is glued onto his neighbour S2. S2 is just a copy of C2. Right? And if I take one of these monomials, for example, and one of these monomials, then this one here is 0 along there, and this one there is 0 along there, so this product, this times this equals 0. I hope this is okay. Well, of course, I'll do more concrete examples later. So then it turns out that, yes, okay, so let me say, first of all, this T, who T is. So then T is a toric, a union of toric surfaces, and it's a Gorenstein variety. Reducible, of course. And T has an action of this big torus. So T is, the torus here is C star to the 4th. Namely, I do the C2, the C star squared acting on S1. Well, actually, there's a separate C star squared acting on S2. These are just diagonal matrices, diagonal non-singular diagonal matrices. C star acting on S3. Similarly, C star squared acting on S4. So this is an 8-dimensional torus. However, I'm identifying the xk. So I'm looking at the guys that, so these two guys act the same on xk. And these two guys act the same on YL, and so on. Right, and so the thing that's left here is a four-dimensional torus. So this is like this torus, this big torus here will be the big torus of this toric fourfold when I've constructed it. So it turns out that T has an equivariance toric deformation smoothing the xk and yl axes and making V irreducible. This corresponds to matrices R, A, B, S in SL2Z such that A is congruent to alpha mod R and B is congruent to beta mod S. Right? So I told you I have these R and alpha here, and I have R and S and beta there. Right? And so I have to be able to take these alpha and beta and combine them together into one single SL2Z matrix. Right? This works if and only if either alpha divides RS minus 1 or beta divides RS minus 1. Right? So if I start off with this tens and I ask, is it possible to make this nice deformation to something that smooths these two top corners and that makes the whole thing irreducible, then the answer is if and only if I can lift it to a matrix. I can lift the values of alpha modulo R and beta modulo S to these numbers here with AB must be greater than 0. Well, let me write greater than or equal. A and alpha and beta are co-prime in any case. Okay, so of course I want to give an example because otherwise the theory doesn't make any sense. So I'm going to do this particular case, and this particular case is going to continue next week's lecture as well, in 2 weeks' time. So I'm going to choose 2, 4, and 3, 2, 2. Right. So what this picture means is I've got the coordinates are x0, x1, x2, x3, and y0, y1, y2, y3, y4. Right, and I have these equations. I have the equations x0, x2 equals x1 squared, x1, x3 equals x2 to the 4th. And down this side similarly, let me write them out because I need them. y2, y4 equals y3 cubed y2 squared, y1, y0, y2, y0, y2 is y1 squared. Right, and then I have all these equations saying xi, yj equals 0 if ij is not equal to 0, 0 or 3, 4. Yeah, and so this is, if I've got it right, this is a seventh of 1, 2. I ought to be able to figure this out for myself. What is 2, 4 is 2 minus a quarter is 7 over 4 is 2, 3, 1. And this is something similar. Yes, and so how am I going to write down a toric fourfold? Well, let me tell you first in a kind of simple-minded calculational way how to do it. So what I'm going to do is I'm going to decorate the diagram with some more tags. I'm going to write down A here and 2, and B here and 1. Yeah, and so what this is, what those numbers at the top are is a recipe for how I intend to deform the equation. So I've got the equation x2 y4 equals 0. I'm going to deform this to x3 squared times a. Okay, so the 2 here is this new tag that I put there, and then the a is a deformation parameter. So, you know, in our notation we need words for this. So this is a tag, and this one here is an annotation. Annotation, it means the same as tag. It means a label. Yes, and so I'm going to and then I'm going to take this equation x3 y3 equals 0, and I'm going to replace it by y4 with exponent 1 times b. Right? I'm doing a little bit of magic here that I'm not telling you about. Yeah? And so why is this good? Why does this solve the problem? So we're doing toric geometry. So then I say that x3, y4, a and b, base z4 equals m, a lattice of monomials. So in toric geometry, I give you a lattice, and then inside that lattice I give you a cone. Right? So this is perfectly clear, simple lattice. Okay? Now, I want to know what are all the monomials in the cone sigma alpha, sigma AB. Right, so sigma, this VAB here will be spec of the ring, which is the semigroup ring of sigma AB. Well, the answer's already on the board. Namely, x3, y4, a and b are the given basis of this lattice M. So if I want to know who x2 is, let's look at this equation. x2 equals x3 squared times a y4 to the minus 1. Right? So I told you how I intend to deform this equation at the top. Yes? And now the next question is, who is x1? Well, I also told you what the answer to that. x1 is, so there's a tag of 4 at x2, so I'm supposed to take x2 to the 4th. Well, we already know who x2 is. Yeah, so I'm taking x2 to the 4th, and then I'm dividing by x3. So the thing I'm writing down here is x3 to the power of 7, a y4 to the minus 1, now to the power of 4. Yes? And x0 exactly the same. x0 is x3, so I'm taking the square of this minus that, that's 12, and then I'm taking the square of this minus that, that's 7. A y4 to the minus 1 to the power of 7. Okay, and now I do the same thing with the y's. So, sorry, there are some different kinds of mathematicians, and I'm the kind of mathematician that likes to calculate. Okay, so the same way, who is, we already know who y4 is, but who is y3? Well, y3 is given by this equation. So he's y4 times, and then b x3 to the minus 1. Yes? And then, so who's y2? Well, there's a tag of 3 at this y3. Yeah? And so I have to do y3 cubed and then divide by y4. So I'm getting y4 squared here. And then this is going to be b x3 minus 1 cubed. So then there's y1 and y0. And these are, because of the 2's there, because there are 2's, this is just an arithmetic progression. So I'm doing y4 to the power of 1, to the power of 2, to the power of 3, to the power of 4, and then this b x3 minus 1 to the power of 5, b x3 minus 1 to the power of 7. Yeah, so completely concrete calculation. So, in other words, so this sigma AB is the cone generated by these. So here's lattice M, and here are these vectors coming out of it, and then so sigma AB is the cone generated by x0, xk, yl down to y0 and ab. Okay, so who is the variety VAB? Well, what I need to say is not just what all the monomials in VAB are, but what all the relations between the monomials are. Right? And so some of the relations are already written down here. They're just the obvious ones that come from the way I derived this. However, there are others which we need to check. So, for example, let's ask, who is x1 times y0? Right? That's this x1 times this y0. In the original variety, in the original tent, the product x1 times y0 was 0. And if he's still 0, then we've lost. If we won't have an irreducible variety. So who is x1 times y0? Well, I've got a formula for x1 here and a formula for y0 here. Yes? And what do you notice? There's x3 to the power of 7 times x3 to the power of minus 7. Yes? And then there's y4 to the power of minus 4, and then here there's y4 to the power of 4. Right? So this is very convenient. This turns out to be a to the 4th b to the 7th. So in other words, this reducible equation, x1, y0 equals 0, which was defining an ordinary double point in codimension 1, is now defining this, well, basically complicated equation, but he's non-singular. I mean, this one doesn't contain, so this does not contain it. So the x0 axis is not there, is not in this variety. Right? So I start off with a deformation that looks like this, and then after I've deformed away, I'm looking something like this. So it may be some kind of complicated singularity near the origin, but I've taken myself, I've lifted off away from the x0 axis. Right? And then who is x, this is the interesting one, who is x0, y1? Well, you know, there's some big numbers on the board here. I don't know if anybody's ever seen numbers as big as 12 in a maths course. x3 to 12, x3 to the minus 5. So this guy here is equal to, what did I say? 12 minus 5. x3 to the 7th y4 to the minus 7 plus 3, y4 to the minus 4, and then sprinkling of a's and b's, a to the 7th, b to the 5th. Everybody agrees? And so this guy here is, well, I don't want to see all these x3s and y4s, and I certainly don't want to see negative exponents of them. On the other hand, I can just substitute this guy here. Right? This is y0 to the minus 1. Right? The power of y to the 4th here is the exponent 4, and here is minus 4. Here it's minus 7, here it's plus 7. Right? So this is y0 to the minus 1 times a to the 7th, b to the 12th. Yes? And this means that also at this far corner here, well, now this contains, if I'm looking at a point of the y0 axis, not the origin, then this y0 is non-zero. Right? And so I don't care the fact he's got a negative exponent. This is some non-zero number times a to the 7th, b to the 12th. And this means that, so now here, I had something which was reducible, and now looks something like this. It has some singularity along the y0 axis. Right? So this is, of course, not a very good equation for an algebraic variety, because this is not a polynomial. Right? On the other hand, because I've got x1, y0 here, I can just replace y0 by x1 to the minus 1. So this is x1 to the power of 1, and then times some power of a and b, which is probably a cubed, b to the 5th. Okay? So the consequence of this calculation is that now sigma AB inside M, so inside MR, so this is a monomial cone, is the monomial cone of an irreducible toric variety. VAB. Yes? So there was a kind of little surprise that I had to do. So, when I was calculating these x2, x1, x0, there was no choice involved. I just have to write these down, right? And so which monomials I'm talking about inside there is already determined in advance once I've chosen these, these conventions about what I'm going to do at the top corner. Right? However, it is a surprise to see that actually we've also managed, we haven't smoothed the bottom corners, but we've got rid of most of the singularities here. Actually, we have smoothed the x0 axis, we haven't smoothed the y0 axis. The y0 axis is transversely like this. Okay. So this is, this is, I've started off with a reducible surface, and I've taken this out now to VAB, which is an irreducible normal toric fourfold, and if I set A equals B equals 0, this gives back T as the 4 strata, as 4 of the strata. Okay, so I want to do this just a little bit more generally than this, so you can see what's happening. But the kind of computational thing, why does this work? What's special about the numbers I chose that makes this work? We're going to need this not once, but time and time again in next week's lectures and the week after. What makes this work? Is that so here I have 4, 2, 4, and I artificially put here a 2 and a 1 there, and then I have 3, 2, 2. The thing that makes it possible to put in these equations to make an irreducible variety is the fact that if I do 4, 2, 1, 3, 2, 2, in other words, I take these numbers and I read them around there. This guy here is a continued fraction expansion of 0. Yes? So remember, I have this little method. I want to cancel the 1. So if I cancel the 1, I get 1, 2 here. Right? And then I can bring down the 4 and cancel 4, 1, 2 to give 3, 1. And then I bring down this 2 and cancel again to make 2, 1. I bring down the 2 and that gives 1, 1. And this is 0. Okay, so this is this little trick of reducing continued fractions. So it's saying that 4, 2 and 3, 2, 2 are complementary continued fractions. Okay, so let's try and remember what this is. This is 7 over 2. 4 minus a half is 7 over 2. This is 3 minus 3 minus a half minus a half minus a half. So that's 2 minus. This is 2 minus a half is 3 over 2. 3 minus 2 over 3 is 7 over. Can anybody do this? 7 minus 3 minus, oh good. I want it to be 5, but actually it's 3, so I've done something wrong. Oh, it doesn't matter. I probably have one of them upside down. It's not important. Can anybody see what I'm doing wrong? 3 minus 1 over 3 halves. It looks like 7 over 3 to me. And this one looks like 7 over 2. Maybe I should have done something else. Maybe I should have included the first 2. You know, I should have, if I wrote this in the other order, it would be 7 over 4. That's probably 2 minus a quarter, 7 over 4. 7 over 4. So this is R over A and R over R minus A. Okay, so let me tell you the general case. As you saw, when I calculated these equations, I had in the reducible variety, when a and b are 0, I have x1 times y naught equals 0, and I replace that by x1 times y naught equals some power of x naught times a to the 4th b to the 7th. And the power I write down here is 0. Right? And so these are in brackets because they're not, it's not something that's specified in advance, it's something that's forced as a result of a calculation. In the same way I have minus 1 here. Right? So these are the corner tags. So that's the thing here. So this x0, y1, we're interested in this equation in the neighbourhood of the y0 axis. So we intend to put y0 equals some value here. Right? So this is the singularity along the y0 axis is x0, x0, y1 equals some constant, and then a to 7th, b to 12th. So this is sort of nice complicated singularity, compound Duval singularity of type an. Right? And then, you know, the x1 is the same. x1 is just x0 to y0 to minus 1 times some power. Right? This says that VAB is transversely x0, y1 equals a to the 7th, b to the 12th along the y0 axis. Yes. So now I want to do the same thing in some kind of generality. So we will have next time we will have you know, not one of these rectangles, but 2 different rectangles. And so we want to understand, we want to sort of write it down in a way that can be treated not just in one example, but sort of analytically, not by a lot of calculations, but by making some theoretical statements. So our trick here is if I want to take A, B, R, and S in Z greater than or equal to 0, actually always greater than 0, except in trivial cases. Right, and I want that RS minus AB equals 1. Right, so this means that R, A, B, S, and S minus A minus B, R, and several others are in SL2Z. So when I was talking toric geometry, I had this lattice M and the dual lattice L, which are always isomorphic to Z2. And then the game of toric geometry is choosing bases in lots of different ways of these lattices, right? And so these matrices are what we use to do this, right? And so I'm going to draw this funny picture on the blackboard. So there's a psi and an eta. These are monomials. They're monomials that base a lattice. And then there's x naught and y naught. And I'm going to have x1 and various other xi's here, and yi's there. So what this picture is, psi and eta is a basis of Z2. Right, so I've drawn it here in a sort of convenient way to be nice and small and compact. I'm thinking of this as corresponding to the coordinate ring of S2. Right, and then I specify x naught equals eta to the minus r psi to the a, and y naught to be eta to the b and psi to the minus s. Yes, so can you see what's happening? I'm just doing coordinate geometry in the plane. These two guys here are a basis of the coordinate plane, and then I'm choosing some basis, some guy over here, x naught. And so the x naught has a positive coordinate psi, so he's in that direction, and a negative coordinate eta. Yeah, and similar y naught has a y naught is over on this side. Yeah? And so what am I doing here? I'm taking the plane, and I've divided the plane into 4 pieces. One of them is called S naught, one of them is called S1, and next one's called S2. That was the basic one we started with, and this one's called S3. Yeah, and the picture looks completely unsymmetric, and it is completely unsymmetric. Right? So I've made this using these. So because these two matrices are in SL2Z, it so happens that psi naught and that x naught and y naught is again a new basis of the space. Right? However, so the thing I'm doing here is again and again I'm choosing this lattice is called M bar. There'll be another lattice called M. Right? And so you can calculate that then eta is x naught to the minus s, y naught to the minus a, and psi is x naught to the minus b, y naught to the minus r. So look, the thing we're doing here is SL2Z linear geometry. So according to SL2, any two bases of the lattice M bar are congruent. This is just a copy of Z2, right? But nevertheless, if I draw a cone in there, it's got convexity properties. And the convexity properties this picture has is that if I take the negative of any of these vectors here, right? This is a bit like the kind of big cone in a root system. All of the negatives of those are all contained in this one cone. So this cone x naught, y naught here is a very big cone. It's, when you draw a pie chart, say how much this is like this, right? And so if I have all of the xi's there, minus xi here, the negative of every vector in the top 3 cones is in cone of S naught. Right? And that's exactly the thing that corresponds to this negative exponent here. So there's an exponent 0 there, an exponent minus 1 there. And it's telling us that when I make this division of the plane, I get this picture here where the thing at the bottom is very big, and each of the cones at the top is just a small fraction of this pi. Yes? So, if you think about it, these two vectors here are inverses of one another, and they're the coordinate transformations between some of the bases here and some of the other bases. So let me try and get, let me try now, I want to say what is S1? So, S1 there is a cone, the cone marked S1 is the cone in M bar generated by x naught and psi. Right? So this x naught and psi they're two linearly independent vectors in M bar, but then they don't span, they're not a basis of M bar. They base a sublattice of index R in M naught. So then the lattice M bar is generated by x naught psi and y naught to the minus 1, which is x naught b psi to the power of 1r. Yes? Or by x naught psi and eta, which is x naught to the minus a psi a. Sorry. Y naught to the minus. I'm sorry, have I got this? So look, the thing I'm doing is completely elementary here. I say, take a lattice M bar with basis psi and eta. Using these two matrices, set up this new vector x naught and y naught, given by these equations. Right? So this is just coordinate geometry in the plane. Then I say, let's look at this cone x naught and eta. So x naught and psi. So x naught and psi, this cone that I'm labeling S1 here. Right? Then I say that this is a cone in a lattice, and so it's got to be generated by primitive vectors along the two sides of the cone, and then by some internal vector. So I say the smallest thing I can do here is do this eta so if I take this guy eta, right, he's giving me a vector somewhere inside this somewhere inside here, a vector which is not in x0 and psi. However, if I add eta to the lattice, psi and eta certainly base the lattice. Right? So this says that S1 is the monomial lattice I'm sorry, this is nonsense. Monomial lattice of 1 over R of alpha, alpha comma 1, where alpha is A mod R. Yes? So what do I want to do? If I take well, the thing I'm doing is I'm considering this cone in the lattice M bar. Then I own primitive vectors along its two edges, right? And so if I take this vector y0 here and just move him one step inside there, so I do a y0 to the minus 1, I get a vector inside there, and x0 and y0 are a basis, and so x0 and this y0 are a basis, and so therefore this cone here is based by x0 psi together with y0 to the minus 1. Y0 to the minus 1 is the thing that's generating the complementary lattice. Right? And so why is this 1 over R of alpha 1? Well, I've got psi 0 and psi. I've got to add one new element here. And so it's certainly a quotient singularity 1 over R, and so the point is that B is alpha to the minus 1 mod R because of this AB, because of this RS minus AB equals 1. Have I got this right? So if I transfer that over to the other side, I've got AB is congruent to it's minus 1. Minus 1. That doesn't matter. Anyway, just do it in an example and you'll see. Okay? So what I'm doing here is a picture of, so earlier I had a monomial lattice. So when I do my tent, right, the tent knows S1, so it knows S0, S1, S2, S3 up to isomorphism. It knows the cones 1 over R of 1 of alpha 1, 1 over R, 1 over S of 1 beta, but it does not know how to put them together. Right? These are abstract toric surfaces, and I just say they glue along the side, and so the whole thing is, I haven't, it's only, it doesn't know the tags. So this is A2 and B1 at the corners, and it doesn't know these tags 0 and minus 1, and these funny paths here, A cubed, whatever it is, A cubed e to the 5, I think, etc. at the corners. Right? So this picture here is putting back in these tags. So the picture here I'm drawing, x1, y0 are opposite vectors, and so the the tag at this x naught is 0. x1 times y naught is going to be some power of x naught, and the power is 0. Okay, so that picture over there is some kind of way of mixing up together these four cones into a single picture. Right, and the toric variety VAB is has cone of monomials sigma AB in MR. Right, so this is Z4 obtained as follows. So what I want to do is take this picture and then start pumping air into him so that it comes out of the blackboard. Right, so this picture is in the plane. It's in this M bar. Right, what I want to do is take the place, this line psi, and bend it upwards like this so that the picture comes out of the blackboard. And the eta also I want to bend up. Right, and so what I'm bending by these deformation parameters A and B. Right, and the picture is very beautiful. I'm not sure if you'll be convinced that it's very beautiful, but I think it is anyway, where I do this. So wait for it. Okay, so the thing I'm asking you to do is to see this as a polytope. So this is a cone in M4. This is a cone in Z4. And I'm drawn projectively as a polytope. Right, so how is this polytope obtained? So the way to think of it is this. You know, the picture, you're supposed to be thinking of this as a picture in 3 space. Right, and so the back of this picture, the place where I have this broken line, the back of this picture is this quadrilateral. Right, so there are 2 quadrilaterals, and then all the front faces are triangles. Right, so the thing is convex. Coming at these lines are coming out of the blackboard. The 2 things at the back are doing this. And so how is this obtained? Well, one way of thinking about it is this. I start off with psi, eta, A and B, and just think of those as generating a simplex. Right, these are 4 vectors in 4 space, so they generate a simplex. Right, then I go along to this face here, A, eta, and psi, and I pull x naught out in that direction. So x naught is given by this eta to the minus, wherever it is. I'm sorry, I have to put in a power of A and B there. I should have. So x naught is A eta to the minus 1 to the power of r. These are the same formulas I had before, times psi to the A. Yes? So what is this? So if you this is a plane diagram. It's one quadrilateral face of this polytope. right? And what is this? What this is saying that the psi naught is linearly dependent on these three guys, right? And moreover, he's a positive power of A, positive power of psi, and a negative power of eta, right? And that means that the picture has the convexity property that you can see here. A psi, and eta are a triangle, and x naught is obtained by pulling that triangle out behind in this way. The only guy with a negative exponent is this eta, right? And in exactly the same way, y naught is eta to the power of b, and then times this b psi to the minus 1 to the s. Right, and so again, the y naught here is, okay, so, we're doing toric geometry, and we have this, the picture is a cone in 4 space, and the cone has these facets, these sides of maximum dimension, right? So, you can one way I've described this here as a convex hull of some points. So this is really very simple. This is psi b eta a forming a simplex, forming the simplest possible polytope you can have. And then I've taken that polytope and I've pulled out its two back sides a little bit. Right? So you can also describe this by inequalities, right? And for that you need, if I can find the page where I've got the So let me I'm sorry, I'm going to stop in 2 minutes. So here, A, B, psi, xeta, psi, and eta base lattice n equals Z4. Yes, and x naught, y naught are in M with the convexity properties you can see. Right, also with this R, A, B, S in SL2. Yes? And the 6 faces of VAB, sigma AB, are dual to, also perpendicular to, perpendicular to 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, R, B, R, S, 1, 0. Just one or two of these are a little bit complicated, and RS, AS, 0, 1, and 1, 0, 0, 1. So, the thing I'm saying is if you take these vertices in this basis, then 3 of them are so the quadrilateral at the back here, right, does not involve any b's. So these are the coordinates here are psi, eta, a, b, and these guys here don't have any b's. In exactly the same way, these guys here don't have any a's. Right, and so on. The others are slightly more complicated. You can and they certainly involve knowing who RABS are. Yes? However, this is a sigma AB, convex cone. And because of this, you have to do a little calculation to verify this. These are the 6 defining equations of these facets of the cone, right? And so this one, and then the four guys at the front you can see. So suppose that I have a monomial in there, which is in the strict interior of the cone. What it means is that every one of these guys is positive on it. This is the last thing I want to say. So remember, you make a toric variety by taking one of these cones and then taking the semigroup of all its monomials and then just taking spec of that. Right? So every monomial M in the interior of sigma AB intersect M is a multiple of AB. Okay, so if he's in the strict interior, then he has to have this. He has to be 0 against this vector, so he has to be a multiple of A. He has to have an A in him. If he's going to be positive against this guy, he has to have a B in him, right? And once that's satisfied, then every one of these guys is positive. Yeah. So why am I interested in this? Right. So therefore, VAB is Gorenstein. Right. So the polynomial ring, the affine coordinate ring of VAB, is the group ring, the semi-group ring of sigma AB. Yes, so I take all the monomials in here, and then I make them into that's a semigroup. I make that into a ring, and then I take spec of this ring. That's who VAB is. And then the omega of AB, the dualizing module, is the interior lattice points. Right? But this very simple calculation I did, just looking at those numbers there, says that any interior monomial is a multiple of AB. Therefore, omega AB is the free module generated by a single monomial AB. And therefore, VAB is Gorenstein. Right? And so when I set A equals B equals 0, I get back to my tent. I get back to the original variety. This picture I drew here in a not very convincing way. If you take this picture and you take AB, we're in a lattice Z4. AB is part of a basis. So if I have a 4-dimensional vector space and a 2-dimensional space, subspace, then I can project away from it. Projecting away takes me to a lattice M bar, which is Z2, based by psi and eta. If you do that, then you get the picture I had over on the blackboard there. Okay, so I'm sorry if this is a little bit rushed and a little bit, not completely convincing. This is part of joint work with Gavin Brown, which we're going to be talking about in the next 3 weeks. If you want a little preparation for that, go to the website, my website, plus 3 folds, plus that graded ring thing, and then there's a long chapter in that about this, about exactly this construction. Yes? So, questions?